In this lecture, I shall identify the main aspect of our new principle of hypercombustion, and then I will show the equipment that we use for its experimental verification. Actual tests with said equipment will be shown in subsequent lectures. The best way to understand our new hypercombustion is to identify the insufficiencies of the combustion of gasoline in all civilian, industrial, and military engines throughout the 20th century up to today. Once said insufficiencies are clearly understood, as far as we are concerned, we shall at least try to resolve them. For our needs, the combustion of gasoline in air can be divided in the following three stages, which evidently occur in a sequence of milliseconds. Stage number 1 is evidently ignition. Stage number 2 is combustion. And stage number 3 is exhaust. To begin outlining this slide, let me recall that the ignition of gasoline in internal combustion engine has been done for over a century via a bipolar, that is, oscillating spark with 20,000 to 40,000 volts, a duration between 1 and 2 milliseconds, and the energy between 30 and 100 millijoules. Note that the sophisticated electronic and mechanical means to deliver the spark in various contemporary vehicles have no impact in our research because we study the spark itself and not the electronic or mechanical means for its delivery. Among the vast literature in the field, I here quote the ignition dream, namely the ideal quantum mechanical combustion of gasoline represented by the single molecule C8H18 with stoichiometric value of atmospheric oxygen and nitrogen. Note in this reaction the absence of nitrogen oxide, because our study deals with the composition of gasoline exhaust prior to the catalytic converter, while, as it is well known, nitrogen oxides are created by the high temperature of catalytic converters. In regards to combustion, let me recall that quantum chemical processes in the combustion of gasoline in air are very complex, numerous, and mostly unverifiable to the best of my knowledge. What is certain is that gasoline combustion occurs at a temperature between 1,800 and 2,400 degrees centigrade, developing depending on local condition, and that the combustion of gasoline in air produces the exhaust contaminants we are interested in decreasing, that is carbon monoxide, CO, carbon dioxide, CO2, and hydrocarbon, HC, that you can see in this reaction. For curiosity's sake, I show here the components of the hydrocarbon with a progressively increasing carbon content, just to recall how many there are. In regard to the exhaust, the information important for our research is given by the average value of the final product of combustion, which include CO2, 13.5%, CO, 1%, of course about 1%, hydrocarbon about 0.1%, plus a number of other natural elements such as water to 12.5%, nitrogen 72%, oxygen 1%, and carbon deposit, which in reality are fullerene. Let us recall that. The data to remember for our studies are given by the spark data, which the spark is bipolar with voltage from 25,000 to 40,000 volts, duration 1 to 2 milliseconds, and energy from 30 to 100 millijoules. Another important data to remember for our studies is the gasoline combustion temperature, which is between 1800 C and 2400 C. We are now in a condition to identify the primary insufficiency of 20th century's gasoline combustion in air and propose its possible resolution. The contaminants we have to decrease, namely carbon monoxide, which is about 1%, and hydrocarbon, which is about 0.1%, are themselves combustible, and their combustion temperature are given by CO has a combustion temperature of 2100 C, hydrocarbons have a combustion temperature of about 2000 C. By contrast, the temperature of gasoline combustion is of the order of 2100 C or 2400 C, depending on the chemical composition of the gasoline itself. Consequently, the combustion temperature of CO and HC are of the same order of magnitude of the temperature of gasoline combustion. Under these conditions, carbon monoxide and hydrocarbons cannot be burned. And in my view, that is the reason why these contaminants have been released in our environment for over 1 century. The solution that I propose is the development of hypercombustion, which can be defined as any possible new combustion which admits, at least on theoretical grounds, gasoline full combustion, GFC, namely a combustion with no combustible contaminants in the exhaust. Gasoline full combustion, namely a combustion with no combustible contaminants in the exhaust. Everything that can be burned should be burned, at least theoretically. For tests done over a decade, a necessary condition for CO and HC to burn is that the gasoline combustion temperature should be at least double their combustion temperature. That is, the gasoline combustion temperature should be minimally of the order of 4000 degrees C. I propose the new hypercombustion because, following extensive mathematical, theoretical, and experimental studies, there exists no known quantum mechanical or quantum chemical process that could increase the temperature of gasoline combustion for up to the value needed for the combustion of CO and hydrocarbon. These findings left me no other option than that of studying a new ignition called hyperignition, realizing full gasoline combustion via the emission of low energy, non-explosive nuclear synthesis in the ignition without the emission of harmful radiation and without the release of radioactive waste. But the needed nuclear synthesis are not predicted by quantum mechanics, as it is well known. Therefore, the need for improving our environment left me to the adoption of the 1935 historical view by Einstein, Podolsky, and Rosen, according to which view quantum mechanics and therefore quantum chemistry are not, I repeat, are not complete theory. I initiated my studies on the EPR argument during my PhD studies in the 1960s at the University of Torino, Italy. Major advances for the completed of quantum mechanics and quantum chemistry occur while I was at Harvard University under a grant from the Department of Energy when the US president was the nuclear physicist Jimmy Carter. Thanks to over half a century of research by mathematicians, theoreticians, and experimentalists from the world over, the new methods have now achieved maturity for application in all quantitative science, including physics, chemistry, and biology, as illustrated by a monograph recently published by the Cambridge Scholar Publishing, which monograph is the main technical reference of our studies on combustion. New combustion is the most recent application of hadronic mathematics, mechanics, and chemistry that I cannot review, and therefore I have to assume that they are known at this moment. In this slide, I list representative references of low-temperature nuclear synthesis which meet the indicated primary requirement for complete combustion. I proposed hypercombustion in the 2019 paper listed here, which suggests, apparently for the first time to my knowledge, the development of an ignition triggering non-explosive and radiation-free nuclear synthesis. The above conception implies the use in hypercombustion of the following low-energy nuclear synthesis. First, the low-energy nuclear fusion. Secondly, the intermediate controlled nuclear fusion. And third, the hyperfusion, which are from which the name of hypercombustion was derived. Low energy nuclear fusion are proposed for the realization of hypercombustion because they are the initiator of the field, thanks to the innovative research by Pons and Fleischmann in 1989. Intermediate controlled nuclear fusions are proposed for the realization of hyperegnition because their molecular rather than molecular structure provides a systematic and controllable exposure of nuclei from their spherical electron clouds, a condition which evidently is very supportive of nuclear synthesis. Finally, Santilli hyperfusion are proposed for the realization of our hyperignition because of the bond within the ignition area of electron pairs with ionized nuclei, which bond results in negatively charged new nuclei, which I call pseudonuclei, that are then attracted rather than being repelled by natural nuclei, by therefore avoiding the Coulomb barrier and therefore favoring the nuclear system by mainly attraction due to Coulomb mutual attraction, under which nuclear fusions are inevitable. In closing, I should indicate that besides no release of harmful radiation or waste, hyperfusion cannot have explosive character because they can only occur under various special conditions we can discuss in technical sessions, such as the number of electrons bonded to pseudonuclei has to be bigger than the atomic number. Then the hyperfusion can only occur in parts per million and other conditions which prevent possible explosions. I now show our hypercombustion experimental setup, which is based on a one cylinder as well as four-cylinder engine. In this slide, we show our hypercombustion testing kit operating on one-cylinder engine. On the right, we show the one-cylinder engine, which is powered by gasoline or methane, and it is commercially known under the name of Predator 6.5 horsepower. On the left, we show our hypercombustion testing kit, which comprises on the top some of the several detectors we use in the test, in the middle our hyper-ignition unit, and at the bottom the variac, which allows test with progressively increasing energy. The power for our kit is given by a conventional 12 volts automotive battery. Note that we show here a kit for testing various engines, with the understanding that once finalized for a given engine, the hyper-ignition can be reduced to a rather modest electronic box. In this slide, we show a close-up view of the hypercombustion testing kit. Note that the silver box in the right is the hyper-ignition unit, which is needed one per each cylinder. In this slide, we showed our four-cylinder modular electric generator under development for local production of clean electric energy with no combustible contaminants in the exhaust. This unit consists of a commercially sold gasoline or methane electric generator, which you can see in this slide. When it is equipped with our hypercombustion unit that you can see in front of the generator on the left and in the back of the generator on the right. Note the presence of four hyper-ignition units, one per each cylinder. Upon completion of its development, our modular electric generator are expected to release 1. Atmospheric gases, 2. Fullerene from carbon deposit, and CO2 that under sufficient funding and academic support can be collected in pressure bottles and recycled via ionization processes into fullerenes, oxygen, and ozone. I now show our hypercombustion setup based on a one-cylinder engine, which is operated by our electronic engineer, Jeffrey Jenkins.
This video is a quick overview of the hypercombustion kit test setup. It consists of a high voltage DC power supply, an energy storage unit with series blocking diode rated for 12 kilovolts and up to 400 amps peak, another blocking diode in series with the magneto on the engine. This makes sure that its output is also unipolar, and it's ORed together with the output from the energy storage unit so that the original magneto can fire the spark plug at the proper time. Once that arc is initiated, follow-on energy is supplied by the energy storage unit. And then a key component is that the high voltage DC to the energy storage unit needs to be interrupted every time the magneto fires. So we pick up the primary waveform from the magneto, and that is used to trigger an optically isolated semiconductor switch, a high voltage IGBT, which then interrupts the output from the high voltage power supply. Everything is monitored up here. We have a forensics detector, 5-way exhaust analyzer, a Fluke DMM for monitoring the DC voltage, and then a Fluke scope meter for monitoring the primary voltage, which is mainly being used as a trigger for the scope. It's not of interest otherwise. And then the secondary or spark plug current, which is of interest. That's the main signal we want to watch. And it is usually displayed on the second channel and picked up by a clamp-on current probe that uses a Hall effect sensor. In the future, we'll be adding a alternator-based dyno. And then for now, this is just the test setup.
Thank you for your attention.